Hello, in this video we're going to be talking about energy transformations. We have some specific ways that we describe, account for, math on when energy changes from one form to another. And here we go. So work, remember, is one of the most important definitions in physics, and it's the transfer of energy. Well, what happens when you transfer energy often is you're converting from one form to another. So we might be changing, from potential energy to kinetic energy or other more exciting things like that. IB exam-wise, the IB will often ask you describe the energy transformation that takes place when blah, blah, blah in some situation. Whenever you're talking about energy transformations, you want to be as specific as you can, especially talk about what type of energy you start with and end with and like where/how that energy kind of is. So we'll look at an example. Let's say, think about this. If you're driving, you hit the brakes on your car slows down to a stop. So think about what kind of energy transformation is happening here. What do you start with? Especially where does that energy go? What do you end with? And kind of how/where does it happen? If you can picture what's going on here. Okay, well, the energy transformation is definitely going to start with kinetic energy. Hopefully that part makes sense. You're moving, so you have kinetic energy. And then the car stops, so you no longer have kinetic energy. Well, where did it go? Did we destroy it? Nope. It turned into heat. Yeah, so heat is thermal energy. It's a type of energy. It's one of the most common types of energy we'll talk about. And yeah, here's the idea. This is a fun picture of brake pads being tested. This is what they do when they say your brake pads are good for however many tens of thousands of miles. They don't really drive them that far. They just put them under extreme conditions like this to figure it out. But there's a brake pad on a wheel going really, really, really fast, so fast that it's got enough friction that it's glowing red hot. But even when you hit the brakes on your car, to a very small extent, this is what's happening. The car, the brake pads rub against the actual, wheel and generate some friction. So they generate heat, which causes your car to slow down. Yeah, so that kinetic energy is turning into heat. And here's where we want to be specific. So the main point probably, okay, if this was an IB question, this would be like 2 marks. 1 mark would probably be for saying kinetic energy turns into thermal energy. And the other mark would probably be for being specific about I had kinetic energy because the car was moving, and then I ended up with thermal energy because I had heat being dissipated by the brake pads. Yeah, so that's the idea. You want to be specific about what type of energy do you have before and after, and where was it? Okay, you try one now. Read this. An electric car starting from rest accelerates up a hill. Describe the energy transformations that take place. So think about this, and the plural there is a clue that there's probably multiple types of energy to be talking about here. So think about how you would say this. Go ahead, pause the video and give it a shot. Here's one way you could say this. You do have multiple types of energy at the end. All right, so we can say the initial part in a few different ways. You could talk a little earlier maybe about energy stored in the battery, but we could say that there's electrical energy happening. It's an electric car, so they're cluing me into something here. So we could say that there's electrical energy just by moving electric charge, by electric current. And that electricity, through the magic of an electric car, is used to make it go. And in terms of go, in this case, we mean 2 things, because the car is both speeding up, it's going from rest to some speed, and it's going up a hill. Yeah, and so it does gain both kinetic and potential energy, gravitational potential energy, we should probably be specific. So there you go, there's another example. We're talking about the type of energy we start with and the type of energy, or types of energy here that we end with, and kind of where they are. We're explaining kinetic energy because it's increasing its velocity, and potential energy, gravitational potential energy, because it's going up a hill. All right. A couple other topics related to energy transfers. One of the main times we transfer energy to make our society work is to generate power, to generate electricity, or um, to, make cars go and stuff like that. And so we use fuel to do this, different types of fuel sources. So one of the big numbers we're concerned with when we talk about different types of fuel and how and where we get our energy is energy density. Different fuels store different amounts of energy. Even the food you eat is kind of fuel. And, like a marshmallow has a certain amount of calories in it, which is a measure of energy. Yeah, you can eat it and you burn it up in your stomach. And you, with the magic of biology, turn that into some available energy for you to use in your body. Yeah, well, like a fork full of pasta probably has a little bit of a different amount of energy than a marshmallow and so on. And so do multiple types of fuels that we use for, like, power generation. So when we talk about energy density, we're talking about energy stored per unit mass. So this will be measured in joules per kilogram. Joules per kilogram is how we're going to do energy density. You might occasionally see stuff like joules per cubic meter as like a volume thing, as a pure kind of similar to density kind of thing. But the IB says they're going to stick with this, and this is usually the common thing you'll see is joules per kilogram. All right, so joules per kilogram is how we measure energy density. And here's some examples. Okay, all of these things store the same amount of energy. So you can see some of these things are much more energy dense than others. Here we have our fossil fuels, which are still one of the places that we get most of the world's energy from burning oil, coal, natural gas. And you can see there's different amounts, like 120 gallons of oil is the same as 1 ton of coal, which is the same as like 17,000 cubic feet of natural gas, it looks like. And fun fact, that's about all that energy is the same amount of energy you can get out of a little pellet of uranium like this in good old nuclear power. Here's another one that shows some numbers with the fun little comic here demonstrating the point. All right, but so like sugar is also, again, a fuel. You can eat a marshmallow, and that marshmallow has something like 19 million joules of energy per kilogram of marshmallow. That's how much is stored inside of it that you could, theoretically pull out by burning it up in your stomach. Coal, fat, gasoline all have different numbers. And so, yeah, these are real numbers. If gasoline has an energy density of 46 million joules per kilogram, uranium does indeed have something like 76 million joules of energy per kilogram. It's very, very, very much more energy dense. They sometimes ask you about this, like what is the most energy dense fuel that we use? Far and away, it's like nuclear fuel. Uranium, if they ask about it, but usually you can just say the fuel that we use in like nuclear power generation and nuclear fission, which we'll talk about one day. But there you go. Energy density is just a way to measure how much energy you get per unit mass of a thing. Another fun measurement we can do when you do these conversions, when you say burn up some coal to essentially boil water and make steam and turn a turbine, or you split the atom to boil water and make steam and turn a turbine. No matter what you're doing, when you're doing a process, you're going to lose some energy along the way. Most of it due to heat, usually, but there's energy losses. There's no such thing as a perfectly 100% efficient process. So we use this word efficiency to describe how much of the energy you start with becomes the useful energy that you want on the other end. So here's the equation in the data booklet. We use this Greek letter eta officially. Looks like a kind of, N with a long leg, but that's officially the Greek letter eta. So there you go. That's the equation for it. It's useful out over total in is really what it is, and it's just a percentage. So useful work out over total work in. We'll do an example of this in a second so you can see kind of what that means, but it just means, okay, how much energy or power, it's a ratio so you can do it either way, did you put in? Like how much, how much energy was available to you from the marshmallow you ate versus how much of that actual energy did you output to like walk up the stairs or whatever. All right, so the useful output is the thing we're trying to do with our energy transformation, and the input is just the total that we started with. we sometimes will see different words to describe the losses, because the idea here is this. This is kind of just not even really a definition. This is just what we mean when we say input and output, and the idea that there's wasted energy. If you just kind of think about how to math through that, it should look like this, right? The total amount that goes in, you have a certain amount of output that's useful, and you have a certain amount that's wasted. So you get your useful output plus whatever was wasted must equal the total that was input. And we'll look at that on a diagram. On a diagram called the Sankey diagram. These are so fun, and they're a good way to visually represent energy transformations. They're pretty simple and kind of intuitive. The one main thing, and the IB does sweat this detail, they'll ask you to draw them occasionally, and they'll give you a little grid paper because they want you to be specific. You show the size of like the kind of arrows, which look like this, represent the relative percentages of stuff. And so let's look at this one. You got inputs on the left is usually the way we'll see it in IB. So they're going to do, here's the energy coming in. Okay, so this is going to be something like your combustion engine in a gas burning car. So we have chemical energy is where that's stored. There's some magical chemistry happening with gasoline that if you burn it, it will release a bunch of energy. So let's say you have 1,000 joules in a certain amount of gasoline. They're showing here all the places that the energy is lost along the way. And at the end of the day, you end up with 340 joules of useful energy. Again, just an example. These numbers are about right, though. You have 340 joules of energy actually used to move the car, which is the thing you're trying to do. So that's why we call it the useful output. But you lose 120 joules from exhaust as a, kind of basically byproduct is the chemical reaction. And you lose a lot of energy due to like friction and heat and all the moving parts of the engine and the car. So you lose most of your energy. And this is usually the case. You lose most of your energy in an energy transformation to heat and other kind of losses like that. If we wanted to do a quick example on this one to talk about the efficiency thing, the efficiency would be my output, my useful output of 340 joules over the input of 1,000 joules. And so I would get that my efficiency is 0.34, aka 34%. And that's about right. A combustion engine is about 34% efficient. About 34% of the available energy in the gasoline is actually used to like move your car. Here's another detailed one, similar idea of going all the way from burning coal at a power plant to a light bulb, making light. And you can see here, there's a lot of losses along the way. You lose a lot of energy delivering power, generating the power. Again, that's all basically heat and friction. You lose a little bit of energy transmitting that power down power lines, a little bit more distribution, wiring. The light bulb itself, we'll look at an example of this in a second, wastes a ton of energy, and you only get a very little bit out at the end of the day. All right, so that's another example of a Sankey diagram. That's what they look like. And just to clarify this part about the whole size of the arrows thing, this is what we kind of mean by the grid thing. If you look on this example one here, they're kind of showing the proportions, yeah? So this guy is going to be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, big grid lines wide. So that 10 is representing like 1,000 joules here. Well, this arrow, and it's like from the actual thick part of it, is going to be 1, 2, 3.4 wide. So that's showing 340 to 1,000. So you draw them relatively, proportionally the size that they should be, like this way, this way, this way. Okay, so let's just do an example problem, a simple one here about efficiency. So we have an incandescent light bulb, which is like, a traditional filament light bulb with a 50 watt input rating, which means the light bulb is going to draw 50 watts of energy, electrical energy from like the outlet. So that's the input. And if the bulb outputs 600 joules of light energy in 2 minutes, what is the efficiency of the bulb is the question. Okay. So think about how you would set this up. If you want, go ahead and pause it and give it a shot. There are really, I think, two kind of good ways to do this, because you could do it with work or you could do it with power. We have two different things here. We have energy and we have power. The most important thing beyond all this efficiency stuff is that you are cool with watts versus joules. That's the most, truly, probably the most important thing, like in all of IB physics, for you to know about. So make sure that you are crystal clear on watts versus joules and what they represent. Watts is power, and the main thing is a watt is a joule per second. So I'm going to do this first in terms of, I think I'm going to do work. I think I'm going to do energy. So let's do my input. I have 50 watts. I want to figure out, because the key thing is I have a time here. So my input power is 50 watts, so 50 joules per second. Yeah, and I know that's delta E over delta T. That's kind of my definition of power, the rate at which work is done, the rate of the transfer of energy. If I want to find how much energy went in, I'm going to multiply by time. It's pulling 50 joules per second of energy from the wall. I'll wait to label this until we do the math. And then I lose a certain amount, and I end up with 600 joules actually turning into light energy. So how much is this? Well, I would just multiply, right? Power times time to get the amount of energy out. 50 watts is 50 joules per second. If I multiply by time, I'll get the power, or sorry, the energy. Now I just got to be careful because I got 2 minutes. I should probably make that seconds, since a watt is a joule per second. It's 120 seconds. So when I multiply these together, I get an input energy over those 2 minutes of 6,000 joules. And these numbers are about right. So I have 6,000 joules of heat, of like electrical energy coming into the light bulb. Only 600 make it out. So my Sankey diagram might look something roughly like this. Here's what comes in. Here's what goes out. All the rest is lost due to heat. Because an incandescent light bulb, if you turn one on and touch it, it's hot, hot, hot. These things lose most of their energy, like 90% of their energy, give or take. They do lose to heat. And anyway, we should finish off the problem here because we want to find the efficiency of the bulb. So I'm going to use the efficiency equation that I do. I really, truly just think of it as output over input, because you can do it with power. You can do it with energy, with work. So I'm thinking I have 600 joules of output divided by 6,000 joules of input. So I do indeed have a 10% efficiency, 0.1, right? That means 10%. 10% efficiency of a light bulb, that's about right. That's a big reason why, you're seeing there's a lot more LED bulbs being used and things like that that aren't incandescent, because you're paying, to make light with a light bulb where only like 10% of the energy that you put in is doing the thing that you want it to do, which is making light. All the other energy is just warming up the room. So there you go. That's how to do efficiency. And just to show you that you can do this two ways, the other option would be to say, what's the output power? And I could do joules per second. So the output power would be, I have 600 joules of power that come out in 2 minutes and 120 seconds. And so the other way to look at this is my input power is 50 watts. My output power is 5 joules per second, so 5 watts. And same idea if I do out over in for efficiency. I'm going to get the same thing. I sure should, because I got 5 watts coming out, 50 watts going in. In other words, 5 joules per second out, 50 joules per second in, gives me the same 10%. So there you go. That's the idea of efficiency, how we keep track of how efficient and energy transformation is when we're turning one type of energy into another. So there you go.